Oh, yes. Okay. Oh, that's great. All right.
You.
Let me share. Okay. That's okay. Thank you for your waiting. So, hi, hello. My name is Hiroshi Idzuchi. So, thank you for inviting me, especially Ahmed and organizers. And now I wish to share my recent studies. So, so let me, okay. So about two-dimensional ferromagnet on chromium germanium tellurides. So I think most of you are familiar with 2D materials, and I know so already other invited speakers uh, introduced very nicely. So I will more focus on this 2D ferromagnet chromium germanium tellurides. So in atomically thin 2D Pandelwas materials, chromium germanium tellurides is a one of prototypical material. So it's reported in 2017. A key feature is we can cleave down to atomically thin limit while we can keep ferromagnetic behavior with high crystallinity. So this is say number of layers versus Curie temperature, and this is MH curve by measured by Mock. So this kind of feature can be seen in many of 2D Van der Waals magnet. But also, I wish to note, so in chromium germanium tellurides, somehow we have relatively easy handling. So like it's less air sensitive. So compared to chromium iodide. So that's why I prefer this material so far. And however, we can basically, try our important challenge. So in 2D Van der Waals ferromagnet, generally, we have a problem of relatively low Curie temperature. In this case, just about 60 Kelvin. And also, until recently, we didn't have spin-dependent tunneling via atomically thin ferromagnetic crystal. That means particularly using Van der Waals heterostructure, not using cobalt or conventional magnet. And I wish to deliver two topics today. So one is increase Curie temperature twice by using heterostructure strategy. So we have reported before, but we have a major update. So let me introduce this study. And also we have another topic is spin-dependent tunneling. This is reported last year, but I think it's not very. I didn't talk a lot on this, so maybe this is good opportunity to share this result. So first, I wish to talk about this spin-dependent tunneling study. So now my approach is using superconductivity to utilize magnetic insulator. So it might be a little bit strange for some people, but I think if we just want to detect spin polarization, superconductivity is very nice tool. So this forms Cooper pair. So basically, up and down spin somehow locked. So we can it is now very sensitive to magnetic field. So if we really look into, so in fact, magnetic insulator has potential to have spin polarization, effective magnetic field, or some anomalous Josephson phase, while some other, like while keeping low dissipation, meaning this tunneling behavior is basically bringing low dissipation nature. So, but so far there was a problem of material choice, so it was very limited. So that's one major success case is using europium sulfide, that is ferromagnetic insulator. And back to 1980s, MIT group see some tunneling, spin polarized tunneling using aluminum superconducting lead. And last decade, now people can see Josephson effect through this semiconducting ferromagnetic layer, that is gadolinium nitride, and see very nice future that probably that is interpreted with spin polarization and effective field. But as I mentioned, the material choice is rather limited because tunneling needs very thin layer, but thin layer, it is hard to grow. But now, in the age of this 2D magnetic material, it is very easy to have very thin layer. So now it's our 2D material gives immediate solution for this problem. So now we can try. And another point of our study is actually using Ising superconductor that is very abundant in 2D materials family. So this is most famous in niobium dicyanide case, and spin is actually locked in perpendicular to 2D sheets, so basically plus D and minus D near the Fermi level. So now the spin is now really sensitive to this D direction spin. In the we can imagine there is this chromium germanium tellurides here, and then these Cooper pair should be sensitive to this CGT's spin. And also in practical, we can we confirmed that we can build a very sharp interface using these 2D materials like niobium dicyanides. So we can now just insert chromium germanium tellurides here. So general motivation is here, just to remind what I talked. So now we want to study spin-dependent coupling in atomically thin 2D van der Waals interface. In this, using this 2D, we don't restrict to CGT, but basically 2D ferromagnetic layer. And whether we can see any new effect, that's our question. And the answer is yes. So I'm not sure how familiar with the Josephson junction. So the structure is here. We have niobium dicyanide up and bottom and top, and we have inserted CGT layer, and then we measure the resistance of the junction. So this is a typical signal. So x-axis is a bias current, and y-axis is voltage drop across the junction. So you see very clear zero resistance state. That means we have indeed Josephson coupling between two niobium dicyanides across this monolayer CGT or six layered CGT. So if you bias more, at some point you break this, the energy exceeds Josephson coupling, and then you have normal state. So you have usual resistance of the junction. So first we confirm Josephson current, and then we also study thickness dependence and characterize thickness characteristics. So we have some resistance coefficient of tunneling behavior, and also thickness characteristics, which is about 1 nanometer. I don't skip the I skip the detail, but with gap size and so on, it's reasonable. And then if we see the critical current with various magnetic field, in fact, actually we have some hysteresis. That's something somewhat unusual. So from here, of course, if you decrease the magnetic field, critical current is higher, but at some point it jumps, and there is a hysteresis. also that kind of hysteretic behavior, or actually implying two energy level, that is seen both 6 monolayers case and monolayers case. And we wondered what it is, and then we constructed actually squids with this CGT tunneling junction. So this is to explain basic principle of Josephson, squids with Josephson junction with zero phase and pi phase. So if you have if your squid has two zero phase Josephson junctions, you have a maximum current at zero field, while if you have zero pi junction, your critical current is minimum at zero field. And so finally, we make this squid. Now one arm has niobium diselenide junction without CGT, and another has one monolayer CGT, and we have nice oscillation and some anomalous behavior. Sorry, this is a monolayer. It's typo. But all right. So we have again, if you have sweeping, if you sweep different weights, you have also different critical current. So all these indicate some kind of two energy levels behavior. And finally, so we make this aluminum, this sample. So we have this squids, niobium diselenide CGT squid, and also several aluminum squids, so that we know exact zero field limit. So otherwise, it's very hard to distinguish the phase, because important is where is this zero field. So by calibrating zero field with these several devices, we finally actually find both phase is neither zero nor pi, so it's very non-trivial. And then actually we had kind of hard time why it happened, but finally we found how can we explain. So if as I said, the Ising superconductivity is very sensitive to plus minus d spin, so you can have this spin-dependent coupling, spin-dependent tunneling. But if your CGT magnetization is z direction, but if your CGT magnetization is in plane direction, this doesn't really have spin-dependent coupling. So this can explain as follows. So actually, so this with magnetic domain structure, we have pi part and zero part, and if you have the energy of pi part and zero part, actually we have some bistable this kind of energy, and then in fact, this can be applied for the area within the coherence length, but this coherence length is rather high, so we can apply this theory. And in experiment, we can do actually measure many times sweeping, and then take hysteresis, and then we can actually confirm whether this is consistent or not. So now we can have two different statistics of escaping from the potential well. So this indeed is consistent with what I explained. So in this part, I have shown the doubly degenerated phi Josephson junction. Phi is meaning it non-zero phase, non-pi phase, some phase between them, and using that is shown with using atomically thin niobium diselenide and CGT, and that explained by coherent combination zero and pi Josephson junction segment. So broad message is all right. We have many interesting 2D materials, so we can actually have many potential further improving or further finding novel phenomena. Now the time is rather limited, I would think, but let me introduce this. So I think this basically explains. So last half part, I wish to explain the approach to enhance the magnetism in 2D material. So people use electric field effect, for instance. It is successful for iron germanium tellurides, but also use pressure cell. So you can apply pressure. This is conventional method, and you can change the atomic distance between the lattice. And although the Curie temperature change is small, but we basically we do, and there is rather limited capability of this stretching. So I think we believe this actually can happen in our sample. So this is rather incidentally observing, but before we were studying CGT flake with nickel overlayer. And nickel overlayer, with nickel overlayer, somehow we have additional optical contrast. And then we examine by AFM and see some topography. Actually, the height is high in this additional place. And then we also do cross-sectional TM imaging, and actually, indeed, this has some structure corresponding to this area. And if we measure Curie temperature with a lot of the CGT nickel flake, and then it seems the formation of this link is somewhat correlate with enhancement of Curie temperature. And there is a story on DFT calculation, so that this indicates lattice stretch may enhance the magnetism. So our hypothesis is here. So if we have some two layers, somehow if we can stretch, so the top layer, it can have wrinkle. So suppose number of atoms is conserved. So if this area is stretched, somehow this area needs to have wrinkle. So we have characterized by Raman spectrum. Raman spectrum shows very good features, and peak position varies with place, and this indicates actually near this wrinkle lower frequency. That it means tensile strain. And also we have measured a lot of sample and show some correlation. That means basically with wrinkle we have a lower frequency. And we have some correlation with Raman and Mach. So if we have more stretch, somehow we have more higher Curie temperature. That's what we have seen. And we see more device characteristics that basically same thing, but for more devices. And then DFT calculation was done for thicker CGT instead of monolayer CGT reported. And also with tensile strain, we see enhanced magnetism in this either magneto-anisotropy by crystal or exchange energy or even Curie temperature. Right. So finally, we examined scanning TM by using scanning TM method. So on this strange CGT nickel O. So all right, let me remind, if we have CGT and form nickel O by sputtering, and then we have some strain and some wrinkle structure. But we were always, it's without seeing this kind of structure, it's kind of indirect information. But if we really see this atomic place, although we need to, it's small change. So we just see contrast as a function of the position, and see some oscillation fits as a function of oscillation. and then we can obtain some, actually it indicates larger lattice constant near the interface with nickel. And by Fourier transform, we actually see more clear behavior. So near nickel, somehow lattice is a little bit stretched. All right. And sorry. So this is and we have more going too deep about how does it happen, but maybe we can save it for question. So lastly, let me summarize. So we have enhanced magnetism in CDT nickel structure, and then we observed correlation with enhanced magnetism and Raman shift, and also DFT calculation support enhanced magnetism in stretched CDT. So this perhaps doesn't really need exact combination of material. So it may be wide. I hope this can be widely used for heterostructure of 2D van der Waals material. So thank you for your attention.
Thank you for very interesting talk. So I have like a couple questions.
Yes.
When you mentioned that like when you form the interface between nickel oxide and CZT, that's algorithm in hand, right? And use attribute it to the tensile stress. So what's it like? How stress is basically change the distance and also the bond angle, because that is depend on how the basically chromium distances.
So angle means in plane angle, right?
So did you look into that? I mean, Dept calculation support anything related?
You mean DFT calculation or magnetism?
Yes. Is that change like this, the chromium's tolerance distances, or like chromium's chromium's angle? How it changes?
Okay, so this is, I think it looks more on the distance itself. So chromium, so this kind of compound, chromium major, there is a large antiferromagnetic exchange energy that is actually, that decrease quite fast with increasing the distance. So we think that is a reason why we see increase.
Yes. We also, I mean, look at like the other system, but I think in this case, like chromium's distance is very far away, so typically would not much affect under the tensile strain, but the other would contribute to it. So you may want to look into it. And you only put it to like tensile strain, but since you have like nickel oxide, the anti-ferromagnet, so it has a ferromagnet anti-ferromagnet coupling. So it's a like magnetic positive effect also plays a role here in enhancing the DC and other magnetic properties.
Okay, that's good point. So in fact, some group shows enhancement of Curie temperature with using the coupling between antiferromagnet and ferromagnet. So we also kind of expect it, but so there are some negative data. So for instance, I do not see exchange bias effect, while if we use permalloy nickel layers with same chamber, I can actually see exchange bias. So I don't, so that's why I think what we observed is most likely not because of the from antiferromagnetic behavior of nickel. yeah, but that's a good point.
You have shown some supercurrent images. Can you like how did you compare the supercurrent with other 2D systems that have been used in Josephson junctions?
I myself do not, but yeah, back in these days, so there are colleagues who was using, for instance, graphene HBM for the barrier. So yeah, we have had some discussion.
And how much? How does it compare with those values?
So for monolayer case, actually for CDT, it was rather high. So it's similar to, it was comparable to niobium dicyanide graphene niobium dicyanide device.
Okay, thank you.
Okay.
So I have a very quick comment on the first question. So because yesterday, so I reported our data on the pressure-dependent germanium telluride, where we found the compressive strain, it decreases the TC, it decreases the magnetic anisotropy, destabilizes magnetic color. From that, it could follow so that the tensile strain would indeed, stretching the lattice, would stabilize magnetic color and enhance the TC. So that is somehow an argument which is put forward also by the speaker.
Okay, thank you very much for that precious information. I'm glad to hear you're consistent, our study is consistent.
From University of, and he's going to talk about.
I guess my time is up. So thank you very much again.
Thank you.
Yeah, so thank you for the kind introduction. My name is Klaus. I'm from the University of Regensburg, working in the group of Professor Jaroslav Fabian. I have changed the title a bit to be a bit more generic. I will talk about these twisted graphene CGT heterostructures, but also about other twisted 2D material heterobilayers. So by now, I think we all agree that 2D materials are highly interesting. And on top of that, for every 3D material, we now have a 2D analog, be it metal, semiconductor, insulator, ferromagnet, superconductor, whatever you wish is available. And despite each individual material has highly interesting properties, we can combine them in van der Waals heterostructures where proximity effects play an important role. Okay, it's not working. So for example, if you look into such a tri-layer structure, then the effective Hamiltonian will not just be the sum of the individual ones, but rather it can be heavily modified by proximity effects. And the prototype material that one typically considers is graphene because it has a weak spin-orbit coupling. Actually, you can say it's absent, roughly. And it also has no magnetism in it. Now, one of the spin interactions that can be induced in graphene is the proximity spin-orbit coupling, as we have already heard today. So, for example, if you consider graphene on top of TMDC, in this particular case, it's MOS2, and if you calculate the band structure from first principles, you will find that the two individual dispersions are very nicely preserved due to the weak van der Waals interaction of the monolayers.
And in particular, the Dirac cone is very nicely preserved within the band gap of the TMDC. However, if you then zoom in to the Dirac states, you will find such a splitting of the bands. And this splitting results from the proximity-induced spin-orbit coupling, which is of the Welle-Zeeman and Rashba type. And maybe I'll change this because my smartphone is maybe interfering. Yeah. Now, thank you. Now, another spin interaction that can be induced in graphene is, of course, the exchange coupling. So when you place graphene on chromium germanium telluride, for example, which is a ferromagnetic semiconductor, you will find a very similar situation. The Dirac states of graphene are quite nicely preserved within the band gap. And if you then zoom in to the Dirac states, you will find such a splitting of the bands, which reminds us of the Zeeman splitting from an external magnetic field. But here is not an external magnetic field, it's rather the exchange field originating from the ferromagnetic semiconductor. Now the question is, why is this important? And I think today we have already seen why graphene physics is important. But still, graphene has very nice spin and charge transport properties, and it can be used to perform spin logic operations. On top of that, when you, for example, combine graphene with the TMDC, it can be used as a field effect spin transistor. In this particular case, it's bilayer graphene on top of tungsten diselenide or another TMDC. It does not matter really much. And what is important here is the short rangeness of the proximity effect. So only the lower layer is proximatized. And on top of that, with the electric field, we can then switch the band structure. So we can effectively turn on and off spin-orbit coupling in the transport channel. And this can be used as a field effect spin transistor. Moreover, we have already seen that it can also be used to interconvert between spin and charge currents, such heterostructures. Without the need of conventional ferromagnetic electrodes, we could actually switch between spin and charge currents. Now, this is very nice, but still, we would like to know if we can get another handle on this and somehow control the things a bit more. So we would like to have an on-demand control of these spin interactions and optimize the things for spintronic devices. And one way to do so is via pressure, external pressure. For example, in these experiments, it has been demonstrated that the proximity-induced spin-orbit coupling can be drastically enhanced by external pressure. So what happens? If you place such a heterostructure in a pressure cell, you will effectively reduce the van der Waals distance. Thereby, the coupling between the layers is getting enhanced, and also the proximity spin-orbit coupling is enhanced. And if you then do the magneto transport measurements of such a system upon external pressure, you will find such a crossover from the weak localization into the weak anti-localization regime. If you then do the fitting of these curves, you will find that the Rashba spin-orbit coupling can be roughly increased by a factor of 2 with an external pressure of about 1.8 gigapascal, which corresponds to a reduction of the interlayer distance by 0.3 angstrom, which is around 10% of the interlayer distance. And now the second thing that can be done is, of course, twisting. And the recent tight binding calculations have shown the following. So when you place graphene on tungsten diselenide, then the Welle-Zeeman spin-orbit coupling in graphene will follow this blue line. So we have this intermediate maximum at around 15 to 20 degrees of the twist angle, and it then goes to 0 at 30 degrees, which is due to symmetry. The Rashba spin-orbit coupling does not show such a, say, nice evolution. It stays more or less the same over the whole twist angle range. And on top of that, the Rashba spin orbit field, this in-plane spin orbit field, can be heavily deformed by twisting. So it has been shown that at 0° twist angle, you have such a tangential, typical Rashba field you would expect. But once you twist it to a certain angle, it can become purely radial. Now, if you do actual DFT calculations on large supercells, you will find that the proximity spin-orbit coupling can indeed be heavily tuned, but the results do not completely agree with what the tight binding picture says, because, for example, this Welle-Zeeman spin-orbit coupling has here more or less a plateau and then drops to 0 at 30°. So what is the consequence of this radial spin-orbit field? So if you do spin charge conversion experiments, which we have heard of today, and you have such a typical radial tangential Rashba field, then your spin density that you generate will be perpendicularly polarized to the charge current. This is known as this inverse spin galvanic effect or Rashba-Edelstein effect. No matter how you call it, it's the same mechanism. But if you then switch into this radial spin orbit field, you can also tune the polarization of your spin density that can become collinear to the applied current. So with the twist angle, we have actually a knob to tune the polarization of the spin density. And now let me switch gears and come to the actual things I would like to present, which is the engineering of proximity exchange in graphene chromium germanium telluride heterostructures by twisting. So the situation we have is like this. We fix the magnetization of the ferromagnet and simply twist. On top of that, we can apply a transverse electric field to see how the things can be tuned. And what we do is DFT calculations on large supercells, and then we do the effective modeling of the low energy states. And the situation roughly always looks like this. So the Dirac states are nicely preserved within the band gap of the CGT. And now let me discuss on a specific example what is going on, which is the 30° twist angle structure. So the overall band structure we have already seen. The two different colors correspond to spin up and spin down. And if you then zoom in to the Dirac states for this 30° structure, you will find that the spin down bands are pushed to lower energies compared to spin up. If you place your Fermi level to this dashed line and you calculate the spin polarization that is on graphene, you will find it to be very uniform and negative. And the corresponding model parameters are the same for both sublattices and also negative. Now, where does this come from? If you consider perturbation theory, you would expect that the Dirac states would couple to these energetically closest spin-up substrate bands. However, if you would do that, then the spin-up Dirac states would be pushed to lower energies because energy levels that are coupled repel. However, this is not the case what you observe in the DFT calculation, and it's actually rather the coupling to high energy bands. In particular, you will find such a pronounced anti-crossing of spin-down Dirac states to substrate bands. And this is, in fact, pushing the spin-down Dirac states to lower energies. Yeah, so the coupling is here. And another way to look into this is within the framework of the projected band structure. So this is again the full dispersion, but now decomposed into spin up and spin down manifolds. And the color code tells you something about the percentage of graphene within these states. So blue color means it's pure graphene, red color means it is substrate, and these rainbow colors indicate the coupling. And in fact, for the spin up case, you will find no coupling to these low energy substrate bands, while there is a quite a weak coupling to these high energy levels. In contrast, in the spin-down manifold, you find quite a strong coupling of the Dirac states to these high energy levels. And this is what pushes the spin-down Dirac state to lower energies for this case. And now this is a summary of our most important findings. So for 30 degrees, we have already seen what's going on. We have this negative spin polarization. Spin-down Dirac states are pushed to lower energies, and these are the corresponding exchange parameters for our model. Now, if we go to the 0 degree case, we find exactly the opposite. This is really remarkable. Spin-up Dirac states are pushed to lower energies. And if you calculate the spin polarization, it's again uniform but positive on the graphene. So you can essentially reverse the proximity exchange by twisting. And what is even more remarkable is that at a certain twist angle, this 19.1 degree, you can actually realize antiferromagnetic proximity exchange in graphene. As we can see here, this very nice sublattice character of say positive and negative spin polarization on the graphene. And of course, we did not only investigate these three angles, did the full angle range scan. And what I summarize here is, say, the ferromagnetic and antiferromagnetic proximity exchange as a function of the twist angle. And what we can see here is that the ferromagnetic one can be tuned rather nicely from positive to negative values when twisting from 0 to 30 degrees. This antiferromagnetic proximity exchange arises only for this special twist angle of 19.1 degree. However, I have to admit that this antiferromagnetic proximity exchange is not very stable, so it depends really very sensitive on the atomic stacking that you employ in your DFT calculations. But still, it's a very nice finding. And of course, we did then also check what the transverse electric field could do. So in these two color maps, I again summarize this ferromagnetic and antiferromagnetic proximity exchange as a function of gating and twisting. And most important is, for example, if you look into this range around 12 degree twist angle, then you can actually switch from positive ferromagnetic to negative ferromagnetic simply with the gating. So you can barely see this in this color map, but still this is a very nice finding that simply with the electric field you can switch the proximity exchange from positive to negative in graphene. Now, why is this important? So this can be actually utilized for spin injection and transport. So when graphene is proximatized in the way I've shown, then the density of states will split up like this. And then the graphene polarization as a function of energy will follow this curve. And recent experiments by the FM.We group exactly wanted to show this. So they did non-local spin transport experiments, which we have heard of today. And this non-local resistance signal depends on the injector, the graphene, and the detector polarization. And in this case, they were using non-magnetic gold electrodes, which means that the injector polarization is 0. And this also means that we have only two contributions left, which is the polarization graphene and graphene, this product, which simply gives you a spin-dependent background. And then this remaining product, P graphene, and the detector one. So the detector is cobalt. And now let's see if graphene really is polarized. This is what they measure. At 0 field, they measure a low resistance state, which means the graphene and the detector, the cobalt, are parallel polarized. At some field, the cobalt switches and we go to a higher resistance state. And at an even higher field, the substrate switches, which brings us back to a low resistance state. So when the substrate switches, the proximity exchange switches. And this means also the polarization in graphene switches. And this experiment very nicely demonstrates that we can use proximatized graphene for spin injection without the need of conventional ferromagnetic electrodes. And now in the remaining minutes, I would like to talk about twisted TMDC heterostructures, and in particular, the valley splitting, how we can engineer this. So what we consider are the semiconducting TMDCs, MOS2, MOSC2, and also tungsten-based compounds. And what is most important is this spin valley locking, which we have heard of today as well. And the important thing is, if you do optical measurements, then the plus K valley will react to the sigma plus polarization, and the minus K valley to a sigma minus light polarization. So if you do photoluminescence experiments at 0 external magnetic field, you will find that the PL peaks of the two polarizations coincide, right? Because they are energetically degenerate. Once you crank up the external magnetic field in the out of plane direction, you will find such a very nice splitting of these two peaks, which is known as the valley splitting. And this valley splitting follows this linear trace as function of the magnetic field. Also the G factor plays a heavy role. In this case of bare monolayer TMDCs, this G factor value is around 4. But still, if you apply a magnetic field of 8 Tesla, you get only a valley splitting of 2 millielectron volts. And this is where the proximity physics comes into play. So if you consider a tungsten diselenide on top of chromium triiodine, which is also a ferromagnetic semiconductor, then due to proximity-induced exchange coupling, a valley splitting of around 20 Tesla will intrinsically arise. So these are the data. And so this additional quenching of one photoluminescence peak for the sigma plus comes from the band structure simply. But still, these two peaks are split. That would correspond to around 20 Tesla of external magnetic field. And this is, of course, why we considered this in DFT and checked what does the twist angle do, what does a gate field do to this. And the story goes like this. So if you start with a 0-degree twist angle structure, you can very nicely recognize the band edges of the TMDC here around the K valleys. These spin polarized in-gap states result from the chromium triiodine, which is also responsible for the quenching of the PL peak for one light helicity. And this is a calculation without spin-orbit coupling to really resolve the proximity exchange alone. Now, if you zoom into the band edges, you will find a splitting of the conduction band edge and the valence band edge like this. The spin ordering is the same, and we characterize the splitting by a parameter BC and BV. If you then go to the 30-degree case, you find that the conduction band splitting remains, the spin ordering remains, while the valence band switches sign. So we can again reverse the proximity exchange splitting in the valence band by splitting, which is similar to what we have seen before. And again, we did the full twist angle and gate scan. So the conduction band splitting stays more or less the same upon twisting, but the valence band splitting can be very nicely tuned from negative to positive in this linear fashion by twisting from 0 to 30 degrees. And if you look into this electric field and twist angle dependence, you can find that the conduction band splitting can be tuned in the range of -2.5 to -0.5 millielectron volts, while the valence band splitting can be heavily tuned from about -1.5 to 4 millielectron volts upon twisting and gating. And this has profound consequences for the valley splitting. So the most important result is here. So this is the calculated valley splitting or tungsten diselenide on top of monolayer chromium triiodine when we twist and gate. And the tunability is really giant. So you can go from 0 to 12 millielectron volts in the valley splitting by twisting and gating. These 12 millielectron volts correspond to an external magnetic field of 60 Tesla. And this is really a gigantic field. And this already brings me to the end of my talk. I hope that I could convince you that twisting and gating are two very, very efficient control knobs to tailor proximity physics into the material heterostructures. And with that, I thank you for your attention.
Questions?
In this TMD with proximity effect, do you calculate the anomalous Hall effect? Because if you have such a splitting, maybe.
Yes, one would expect that, right? But we do not calculate it.
No,
So right now we're at the stage that we have calculated all these heterostructures, applied the electric field, explained the mechanism, what is behind this reversal, let's say. But one could do that.
Yeah, because that could motivate, I think, the experimentalists to try, because that's kind of easy measurement.
Yeah, sure.
It's very interesting talk. So you look at like the system that has very low DC, and actually chromium iodide has very low DC.
Yeah, and it's even more unstable, let's say.
Exactly, and very sensitive to the oxygen.
Yeah.
So iron's germanium telluride becomes interesting candidate because it's also have like perpendicular lattice and entropy. And really people also try to basically interface with the tungsten diselenide as well. So that may bring up basically like, you know, close to room temperature, you know, multiple effect. And that could be a very interesting system to look at.
Yeah.
So regarding this TMD, I know some work they show that like on top of basically forming interface with other magnetic materials, you can dope magnetic, you know, elements, and that could also enhance Vallee spin, you know, Vallee splitting. So do you think that would be interesting to approach using two different ways? So one is you dope to enhance that, and then you can form the interface to further enhance Vallee.
Sure. Yes, I think so. Absolutely.
Thank you.
Yeah, hello. So it was a very nice talk. So I have a particular question for you. So like you mentioned previously, like if you put any graphene, very low spin orbit coupling material and TMDC, obviously that will induce spin orbit coupling. Okay. So there are experimental and theoretical evidence that if you put a bilayer graphene on like WaC2, that will actually change the spin orbit coupling of graphene from microelectron volt to millielectron volt, like 15 or 7 millielectron volt. Okay, and also you can tune the spin orbit coupling, and you can actually measure it by doing non-local measurements and other thing. Okay, so people have found both theoretically and experimentally that if you actually tune the perpendicular electric field from negative to positive, the splitting can change from for bilayer graphene from valence band to conduction band. Okay, both like capacitance measurement or normal D measurements. Okay, so my question is, what will happen for monolayer graphene? If you put monolayer graphene on WaC2, what will happen? Because for bilayer graphene, we can understand like the bottom part of the bilayer graphene is basically close proximity to the WaC2. That can actually enhance the spin orbit coupling for the bottom layer. For the top layer, since there is a van der Waals distance between the top and bottom layer,
So overall spin orbit coupling is basically small. So my question is, what will happen for the monolayer graphene? So can we act similar to the bilayer graphene? We can actually switch the like proximity induce
No.
with the perpendicular field.
So there is a small impact of the proximity spin orbit coupling upon electric field, but you cannot switch it because in this sense the bilayer structure is really completely different.
Yeah, I know. So what will happen with the field?
So you mean what happens to the effective parameters once you apply the
exactly. Experimentally for bilayer graphene, people have found like if you have some phase diagram of D versus density, like D is the field, what I'm talking about, and N is the density. If you see the map near the if you the diagonal is basically the Dirac point, okay, the diagonal element. People have found some asymmetric dependence also. The asymmetry is coming from the spin splitting, okay.
Yeah.
So what will happen for the monolayer case?
Yeah, so I guess what happens once you shift, say, the Dirac cone within the band gap, you can tune the proximity.
For monolayer graphene, there is no band gap.
No, within the band gap of the TMDC. So you shift your Dirac states within the band gap, and thereby you affect the proximity spin orbit coupling. This,
how it will depend? Okay, sure. Yeah.
So thanks again for the talk.
Yeah, thank you.
So we have the last talk of the session that is going to be given by Professor Andrei Slavin from Oakland University. He's going to talk about spin torque-driven antiferromagnets for terahertz frequency magnetics.
All right. So I will talk mainly about the application of antiferromagnets in terahertz frequency signal processing. This talk will not contain a lot of new physics. This will be a talk of how to design useful devices in terahertz frequency region from a theoretical point of view. I will talk a little bit about difference between antiferromagnetic materials and ferromagnetic materials, and how the antiferromagnets can be used in terahertz spintronics. I will talk briefly about oscillators made based on antiferromagnets, and a little more detail about detectors. I will talk about the construction of a resonant antiferromagnetic detector of terahertz frequencies. And then I will discuss the tunability of receivers, how you can make this receivers of terahertz frequencies tunable. Before I talk about the motivation, I would like to say that Louis Néel, who basically discovered antiferromagnets and studied them in detail, in his Nobel Prize address said, these are very interesting materials, but absolutely useless. I will try to prove that it is not exactly that way, although making use of them is not a trivial issue. So first of all, we will be interested in a frequency range of about 10 to the 12 hertz, and it is rather easy to generate everything lower and many frequencies higher than that. But there are no natural, practically no natural resonators having resonance frequencies in the terahertz frequency region. And the antiferromagnets are almost the only class of substances which have natural resonance frequencies lying in a terahertz region. What's the difference between dynamics in ferromagnets and antiferromagnets? Well, ferromagnets, they have magnetization, order parameter, and the resonance frequency of a ferromagnetic resonance is proportional to the external field and the dipolar fields, which to a certain extent, these dipolar fields can add also the anisotropy fields, and dipolar fields are also almost totally dependent on the shape of the sample. These are demagnetization. And you see that the external field realistically cannot be more than half a Tesla for any portable device. So the frequencies which you can reach are limited by, say, 20 or 30 gigahertz. So if you want to do something which is higher than that with ferromagnets, you need either huge magnets or there is no way. In the antiferromagnetic substance, there are two sublattices which are oriented anti-parallel to each other. The field which keeps them anti-parallel, this is the internal uniform exchange field or Weiss field, the field which is responsible for ferromagnetic order. This field is about 1,000 Tesla. So trying to interact with this field is almost useless. How big field you can create? 10 Tesla, 20 Tesla, not 1,000. So in some antiferromagnets, you can study statics by changing the external field, and chances to change the dynamics using external field are almost nil. But the antiferromagnetic resonance frequency is determined by the product of this exchange field, internal exchange field, and rather small anisotropy field. And that means that you can influence the frequency of antiferromagnetic resonance mainly by changing the anisotropy field of the crystal. Now, if we want to actually create a generator, we need to somehow excite this eigenmode either in ferromagnet or in antiferromagnet. In a ferromagnet, you can do the following thing. You can actually create the spin polarized current where the vector of polarization will be parallel to the magnetization, and that will create, with a certain direction of the polarization, will create an anti-damping torque, which will try to destabilize the static direction of magnetization, which is actually in a static case simply parallel to the external field. If you will try to do something like that in antiferromagnet, we have two directions of magnetization, one sublattice and the other one. And so if you destabilize one of them, you will actually stabilize the other one. So if you apply the external spin torque or spin polarization, which is parallel to the direction of magnetization, in this case, to the direction of these two magnetizations, the net result will be zero. You will not be able to excite anything. So there is no chance to actually excite the eigenfrequency. So if you want to excite something, you need to do something else. And what can you do? You can apply the spin polarization perpendicular to the direction of magnetizations in the antiferromagnet. Perpendicular, in that case, what you can do, you can slightly tilt the antiparallel directions of magnetization. Can you tilt it strongly? No, because you see that force which makes them antiparallels tend 1,000 Tesla. So you can probably get tilt of 1 degree or couple of degrees. But this is enough. If you do that, the tilted antiferromagnetic sublattices will start to rotate in this huge exchange field. And if you will do that, you will get the rotation of this magnetization order in the huge exchange field, and you will get frequencies of this rotation, Larmor frequencies, which are in sub-terahertz or terahertz frequency range. Now, the question is how to choose the crystal. And there are plenty of uniaxial antiferromagnets, and among them there are dielectrics, and there are semiconductors, and there are conducting materials, and there are also plenty of biaxial crystals where the anisotropy is more complicated. The frequency, the characteristic frequency of antiferromagnetic resonance, you see range from 1 terahertz to say 160 gigahertz. And this is a hematite where the frequency is relatively low. So it is a kind of a proof of principle material, which is a antiferromagnet, but the frequency is still rather low. So you can use almost the conventional electronics to do experiments with. It was shown experimentally that if you put an antiferromagnet in contact with a ferromagnetic material and you excite a ferromagnetic resonance in the antiferromagnet, in the ferromagnetic materials, there will be a spin pumping into the antiferromagnet, and you using inverse spin Hall effect, you can actually detect the signal. And that was demonstrated both in chromium oxide, in manganite fluoride, and in hematite. So there is a chance to receive the external signal using the anti-ferromagnet, and the response will be resonant. And if we find a way to tune this resonance also, then we will get both a generator and a receiver, which is continuously tunable in frequency. So our goal, basically in this talk, I will talk about only receivers, to create a tunable resonant receiver of sub-terahertz signals based on antiferromagnet, to find how it can be tuned, and to find how we can get the output of this material, and how can we excite the signal in this resonator. This slide simply summarizes our theoretical project of how to create a generator. And a generator can be created by putting a layer of antiferromagnet on a platinum electrode, and then the current flowing in the platinum creates a spin Hall effect, which creates a spin torque on the boundary. So the antiferromagnet should be very thin. And in that case, there will be a tilt of sublattices and rotation of sublattices in the plane perpendicular to the hard axis of the material. And the equation which describes this is very similar to the equation describing the oscillations in the Josephson junction, where this one over exchange field plays the role of the effective mass, the effective damping is usual Gilbert damping, and the Josephson potential is replaced by the potential where phi is the azimuthal angle of rotation and of the sublattices. And the frequency, as you see, can be about half a terahertz when the current density is about 10 to the 8 ampere per square centimeter. And we have here a big specialist in spin torque oscillators as our chair, and he knows that in principle you can reach these current densities in real experiments. Now the receiver. We will try to use the receiver using a very similar device. The device consisting of the antiferromagnetic layer, a layer of platinum or any other heavy metal, where we will supply the AC signal, which is the signal which we are going to receive, plus a DC signal, which I will show can help us to change the resonance frequency in the antiferromagnetic material. And the top layer will actually receive the signal obtained due to the magnetization dynamics in antiferromagnet using the inverse spin Hall effect. I will not discuss these equations in detail. I will simply say that this is the equation for the Néel vector or order parameter of antiferromagnet, which is basically difference between magnetization of sublattices. This term is the inertial term, where this is the effective mass. This is a damping term. This is term describing the anisotropy of material, and we will have two spin torque terms, one related to the DC current which we are supplying to move the frequency, and AC current, which is our actual signal. If you do first of all, the static problem, you will see that DC current basically changes the direction of the Néel vector. And this angle is proportional to the current, and that way you change the frequency of the antiferromagnetic resonance. While the dynamic term, AC term, basically gives us the high frequency response. And this high frequency response looks like this. This is a normal resonance curve. As you see there, for the material which we're using here, which is, I think, iridium manganate, the frequency is about 450 gigahertz. Our line width is about 60 gigahertz. And although this Q factor is only around 10, this is much better than bolometers, which are used right now to measure the terahertz signal amplitude. We'll also see that the resonance frequency can be tuned by the changing of a current density. Again, this is not a huge change, but nonetheless, it's continuously tunable. And I saw a new paper submitted to Science where this was fully confirmed experimentally. It will appear probably in a couple of months. The line width is not changing with the current, is almost constant. And the sensitivity of a detector is actually rather large. The sensitivity of a detector, if a detector has a nano size, is about 1,000 volts per watt, which means the millivolts per microwatt, which is comparable to the best Schottky diodes or best GaN diodes used, semiconductor diodes. And diodes are not frequency selective. It is very important to understand that you can get a good receiver in the case when the signal is polarized, circularly polarized, and you will need to construct the antenna in a specific way to get the signal if to get the response if the signal is linearly polarized. And the calculations show that for linearly polarized signal, if you are not using the external bias magnetic field, you will not be able to receive anything in the uniaxial antiferromagnet. And you will need a biaxial antiferromagnet if you want to receive a linearly polarized signal. Circularly polarized signals can be easily received with a good sensitivity. So the intermediate conclusion is that if you want to have a receiver which will work with signals of any polarization, you need to use biaxial antiferromagnetic crystals, and you will increase the sensitivity of a detector if you apply the external bias field. What you can do also to change frequency is to put the antiferromagnet in contact with piezoelectric. In that case, by applying voltage, electric voltage to piezoelectric, you can change anisotropy in the antiferromagnet, and you can change the frequency of antiferromagnetic resonance. And it can be shown that this magnetostriction is different for different crystals. For example, in nickel oxide, it is the coefficient of tuning in 1.6 10 to the -2 kilovolts per centimeter, while in the hematite, it almost 2 orders of magnitude larger. And you can extract the signal either by inverse pinhole effect or using the antiferromagnetic tunnel junction, which recently has been demonstrated experimentally. So my final conclusion is that we demonstrated theoretically that antiferromagnets can be used as active elements in resonant generation and resonant detection of terahertz signals. The sensitivity is comparable to the sensitivity of modern Schottky diodes, and the effect can be observed experimentally. And this is a challenge to the experimentalists who are sitting in this audience and in general. Thank you very much.
Questions?
So thank you for a very interesting talk. So actually, I have a question which you didn't cover so much in your talk regarding the generation of terahertz radiation. So it's correct. So that there is a terahertz gap where generation of terahertz waves is difficult. Nowadays, it's actually not a big deal. So the major issue is that the power of the generated microwave. And can you comment how powerful is your proposed source of the antiferromagnet radiation?
Well, it's a good question. The power, if we are talking about antiferromagnetic device of this kind, the power is determined by 2 things. By the, I'm sorry, I did something wrong. Just hold on. Yeah, the power is determined by the bias current and by the volume of antiferromagnet. If I increase the volume of the antiferromagnet, I will have higher threshold of excitation. So I will talk about the values of amplitude of the electric field amplitude about well, I would say powers in microwatts.
How much?
Microwatts.
Microwatts.
Microwatt, maybe. So it's
would it be possible to achieve milliwatt?
I doubt it. Yeah, it's strongly doubted.
Okay. Thank you.
So microwatts, tunable frequency with microwatts will be a good success.
Okay, very good. Thank you.
Yeah. Yeah. Vincent want to ask me.
In your final slide, you say that to increase the sensitivity, you can include or insert a magnetic tunnel junction. But then, if I'm not wrong, you have like platinum as a second electrode. So how? I don't.
With sensitivity as in a detector, you see the sensitivity depend. Sensitivity. We assumed that the thickness of antiferromagnet is rather small. It's the thickness of a layer is 30, 40 nanometers, not more than that. In that case, you can get the sensitivity which is good, which is comparable to the sensitivity of GaN diodes or Schottky diodes. So there are no miracles here. Because if you will reduce the volume, you will increase the influence of the noise. And signal to noise should be at least higher than 5. So you can't get, without cooling, the sensitivity higher than, say, several millivolts per microwatt. Yeah, I would like to stress one thing. In contrast with many other projects to generate and receive, we are talking only about generators and receivers, which can be continuously tuned. Because it's absolutely no problem to generate terahertz when you, say, have a piece of antiferromagnet and you put an optical femtosecond pulse on it. You will generate continuum. This continuum of frequency will contain terahertz. But how to extract these terahertz, how to select them? You will need a resonant receiver, like what I'm suggesting, or something like that. So it's no problem to generate continuum of frequencies containing terahertz. It's difficult to generate quasi-monochromatic signal in a terahertz frequency range, which can be continuously tuned. The same is about the receivers. Bolometers work pretty well, diodes work pretty well, but they are not frequency selective.